So now we're going to see what happens when we let ourselves escape the limitations of hydroxide needing to be our base and something H plus needing to be our acid. With bronsted-Lowry, we define proton donor as our acid and proton acceptor as our base. Now remember, H plus is a proton. That's a proton with no electron. That's just what hydrogen is. Its ion is, rather. And then hydroxide is still, our proton acceptor. So it still fits into the definition for bronsted-Lowry base. But we're going to see here in 2 seconds that we can go beyond that. So let's take our H3O plus and mix it with ammonia, NH3, and let it go to water and NH4 plus. Oops. NH4 plus. Okay, so what's going on here? We don't have hydroxide, but we have an acid with we have something with an extra proton. That's why we have that plus sign. And we have something that can accept. If we look over here, we see now we have an extra proton where we don't have one here. So we've gained a hydrogen. So this guy is our acceptor. And this is our donor. So one of these hydrogens, let's make it a pretty color, one of these guys is going to go over here. And if we look over here, we now have water. So indeed, we've lost a hydrogen from the acid. And over here, we have indeed gained a proton. So you see that plus sign, that means that we do have an extra proton or less electrons. But in this case, we can see that we have the extra hydrogen. So let's see what happens then if we do something without hydronium. Oh dear. So we're going to see that bronsted-Lowry not only frees us from the restriction of having to be hydroxide, it also frees us from the restriction of something having to be H plus. So NH3 plus water, and we're going to go to equilibrium, goes to NH4 plus and hydroxide. Okay, so what's gone on here? I have NH3 on this side and NH4 on this side. So I am gaining, so I'm an acceptor. I'm accepting. And over here, I'm going from H2 to OH, so I'm losing. So I'm a donor. So that means this is my acid, and this is my base. So I just made water an acid. What? Yeah. So it doesn't have to be a plus, which, you know, is good and it's bad. It's good because it lets us see other reactions other than HCl and NaOH. We're going to see how these acid-base reactions go well beyond those definitions. And we come over here. Now what's going on? I have it in equilibrium, okay? So let me do a different color. Let's go blue. So I have this proton is going to come over here. And oops, wrong one. Wrong way. Warning, warning. This proton, see, I don't even want water to be the acid, is going to come over here to ammonia. And on this side of the equation, then, I am going to take a proton from here and go here. So you can see that it can go both ways. That's where this arrow is. And so what we're saying is that it's not going to stay one dominant species or another. So we're not going to throw things into a beaker and mix them up and end up with only one thing in the end. What we are going to have is a certain amount of our NH3 and our NH4 along with our water and our hydroxide. So these things just kind of keep going back and forth and back and forth. Cool. So that is a bronsted Lowry. So for the next one, I'm going to talk specifically about net ionic reactions. Sorry, I think I'm done for the day. Net ionic reactions, and explain a little bit more what the book's example is with in benzene. Yeah, they had one that they kind of refer back to the beginning of the chapter. So it's a good chance to refresh on net ionics, so you'll be able to keep up with Mr. Evan and Gabbing, and we'll see you on the next one.